Next speaker will be Stefan Ivkovic. Topic is dynamics of operators on the space of Radon measures. You can start.
Thank you very much. Also, I thank very much organizers for giving me opportunity to present these results in this very nice conference. So, as the title says, we shall study the dynamics of certain operators which act on the space of radon measures. Before introducing the results, I need just to introduce some definitions. So, if X is a Banach space, sequence Tn of operators, bounded linear operators on this Banach space is called topologically transitive if for each non-empty open subsets U and V of X, there exists some n such that Tn of U intersected with V is non-empty. And then a single operator T is called topologically transitive if this sequence T to the power n is topologically transitive. Now we have also a more general notion. We say that T is topologically semi-transitive on X if for each pair of open non-empty subsets O1 and O2 of X, there exists some n natural number and some scalar lambda such that lambda Tn of O1 intersected with O2 is non-empty. In the literature, you can also find the terminology topological transitive for supercyclicity, but I prefer this terminology, topologically semi-transitive. And the last concept is what we call topologically Cesaro hypertransitive. This means that for each pair of non-empty open subsets O1 and O2 of X, there exists a strictly increasing sequence of natural numbers nk, such that 1 over nk times T of nk of O1 intersected with O2 is non-empty for all k. So what we can see now is that every topologically transitive operator is topologically semi-transitive, and also every topologically Cesaro hypertransitive operator is topologically semi-transitive. But there are examples illustrating that vice versa does not hold, as we shall see. Also, one more concept which I need to introduce is that if you take X a topological space and you let alpha be invertible map such that alpha and alpha inverse are Borel measurable, then we say that alpha is aperiodic. If for each compact subset K of X, there exists some n constant, such that for all n greater or equal than n, we have the K intersected with alpha n of K is empty. For introducing this concept, actually you don't need that alpha is invertible, but for our purposes, we shall assume also that alpha is invertible. And just also to fix some notation, so here in this talk, at least in the first part of the talk, omega will be a locally compact, non-compact outdoor space, and alpha will be an aperiodic homeomorphism of omega. And as usual, C0 of omega is the space of all continuous functions on omega vanishing at infinity, and this is equipped with the supremum norm. As we could hear in one of the previous talks, this is actually a non-unital commutative C-star algebra. And also we let double V be a positive continuous bounded function on omega, and we will assume that V inverse is also bounded. Then we shall consider the weighted composition operator on C0 of omega with respect to alpha and V. It is T alpha of V, and it is given in this way. T alpha of V is double V multiplied with F composed with alpha. So you first apply a composition operator, composition with alpha, and then you multiply with double V. And it is straightforward to check that this is a bounded linear operator, and it is also invertible because we assume that double V inverse is also bounded. And we shall denote its inverse by S. And it is not hard to calculate powers of this operator and powers of its inverse. And now we can characterize topologically transitive such operators. The equivalent conditions are that for every compact subset K of R, of omega, sorry, it should be omega, there exists a strictly increasing sequence of natural numbers such that the limit when K goes towards infinity of the supremum of this over this compact subset K of this expression here is equal to the limit as K goes towards infinity of the supremum over this compact subset K of this expression here, and it should be equal to 0. And once we have this characterization, then it is also not hard to construct concrete examples. But this shall not be the main topic of our talk. We shall study the adjoint of this operator, which acts on the space of Radon measures. So the adjoint will act on the space of regular Borel measures on omega. This is a Banach space equipped with a total variation norm, because we know that this is actually a star isometric isomorphic to the dual of C0 of omega. And it is not hard to calculate explicitly how this operator acts. So when you apply this operator to any regular Borel measure mu and evaluate in any Borel subset E, then you get this. And similarly, we can calculate the powers of this operator and the powers of the inverse. And now comes the promised characterization of topological transitivity of such operators. So this operator is topologically transitive if for every compact subset, if and only if for every compact subset K of omega and any two measures mu and v in M of omega which vanish on the complement of K, there should exist a strictly increasing sequence of natural numbers and sequences of Borel subsets AK and BK of K such that alpha nk of K intersected with K is empty for all K in N. And moreover, this limit, the limit of the total variation of mu evaluated in EK as K goes towards infinity is equal to the limit when K goes towards infinity of the total variation of V evaluated in BK, and it should be 0. And moreover, we require that the limit when K goes towards infinity of the supremum over the set K intersected with AK complement of this expression is equal to the limit as K goes towards infinity of the supremum over this set K intersected with BK complement of this expression here, and both these limits should be 0. And if we take a careful look at these conditions, these conditions may seem at the first look a bit hard for constructing concrete examples. But these conditions are given in this way because we really wanted to give equivalent conditions for topological transitivity. But if you make these conditions a bit stronger so that they just become sufficient conditions, then this stronger version is easier for constructing examples. And this is what we have in this corollary. So what I do is that actually I simply let AK and BK be the empty sets for all K. And then this limit is always 0 for any mu and V. And then I just have to take care of these two conditions, but then I evaluate supremum over the whole K, because then AK complement is simply the whole omega. And then this makes me easier to construct examples. So just let me read these sufficient conditions. For every compact subset K of omega, there exists a strictly increasing sequence of natural numbers such that this limit over now the whole compact subset K of this expression is equal to the limit over the whole compact subset K of this expression and equal to 0. And then the natural question which arises is, are these conditions, sufficient conditions, really stronger, strictly stronger than these equivalent conditions here? Or in other words, can we find an example where these equivalent conditions are satisfied, but where these sufficient conditions are not satisfied. So this is an open question. But for these sufficient conditions, we can construct concrete examples. And here I shall read one example. If you let omega be the real line, and you let alpha be a translation by 1, and then you let simply W be the constant 2 for all t less or equal minus 1, 1 over half for all t greater or equal to 1, and linear on this interval here. And even more general constructions are possible to be given, satisfying these sufficient conditions. But as you recall, in the beginning of the talk, we introduced several notions of transitivity, not only transitivity, but also semi-transitivity and Cesaro hypertransitivity. And now we shall see how are these operators which are semi-transitive and Cesaro hypertransitive. So this operator is topologically semi-transitive if and only if the same equivalent conditions hold. The only difference now is that we require, when we consider these supremums, that the product of these supremums in the limit when k goes towards infinity is 0. Because here you see that we have that each of these supremums in the limit when k goes towards infinity are 0. Here we have something less. Here we require that the product of this supremum in the limit is 0. And this is why we now will have examples of operators which are semi-transitive but not transitive. And also for Cesaro hypertransitivity, something similar happens. We have similar equivalent conditions, but now we evaluate these supremums with here nk, 1 over nk in front of this expression and nk in front of this expression here. And this is the reason why we can actually prove. I will not have a time to read all the examples, but let me just summarize the conclusion. The conclusion is that there exist Cesaro hypertransitive operators of this form which are not transitive. There exist transitive operators which are not Cesaro hypertransitive, and there exist semi-transitive operators which are neither transitive nor Cesaro hypertransitive. As I said, for the interested people, I can send in the mail examples, but there are such examples which really illustrate this. And the next what we study is also cosine operator function, which looks in this way here. So this operator generates the cosine operator function, which is given in this way. And for this operator, this cosine operator function, it is also possible to provide some conditions, sufficient conditions, ensuring that this operator, cosine operator, is transitive, semi-transitive, etc. Here are some conditions, and it turns out that our examples, which we already presented above, also satisfy these conditions. And this is what I wanted to say about transitivity. Another aspect of dynamics, which can be considered as an opposite of transitivity and chaos, is convergence towards a fixed point. And for that purpose, we shall now assume that omega is a compact Hausdorff space. And now we shall consider the space of all psi and Radon measures on omega equipped with the total variation norm. So then it is a real Banach space. And same as for the complex case, one can show that this is actually the dual of CR of omega, where CR of omega is, as you expect, the space of continuous real valued functions on omega equipped with the supremum Rho, which is also a real Banach space. So its dual is the space of all psi and Radon measures. And what we are going to study, we are going to study the adjoint of the integral operator. So we consider integral kernel, k goes from omega times omega into R, which is supposed to be non-negative, and we let mu be any positive radon measure on omega, such that this is satisfied for all x, so that we can normalize k, obtain k tilde in this way here. And then k tilde is also continuous non-negative, and this integral is 1 for all x. And then you get the corresponding integral operator, which, thanks to this normalization, becomes a Markov operator. And then we can consider the adjoint tk star, which will induce then the Markov chain. And now we want to say when this Markov chain has a fixed point. So when this k tilde in the supremum norm is less than this here, then there exists a unique probability radon measure v tilde on omega, such that this Markov chain converges towards this v tilde in the total variation norm for all probability radon measures v on omega. And there is also a concrete example. If you let omega be this interval and you let k be given in this way here. And finally, for the last 2 minutes, I just want to say that the important aspect of the theory of Markov operators and dynamics of Markov operators is also cones in Banach spaces. And for that purpose, we study some structural properties of cones in the space of Radon measures. So a subset S of a Banach space I is called spaceable in I if S union 0 contains a closed infinite dimensional subsets of I. And for a cone, what we say is a cone, it is a subset B of a vector space I, such that for every scalar C, CB is a subset of B. And now it is not the standard definition of cone. I mean, we usually deal with positive cones, but this is an extended cone, you can say it that way. And in some papers by some Spanish authors, they call this for a cone. And then what we obtain, I shall just read the result. If you let K be a cone in M of omega, in this sense here that CB is a subset of B for every scalar, CK is subset of K for every scalar C, then if there exists a sequence of mutually disjoint Borel subsets En of omega, such that this is not this, then we can obtain that actually the complement of K is spaceable in N of omega. Or without going into details, we introduce some sufficient conditions which ensure that the complement of K is spaceable in N of omega. And the concrete application is that if K is the cone of all scalar multiples of positive Radon measures on a non-compact locally compact Hausdorff space omega, then as you could guess, the complement of K is spaceable in M of omega. And finally, I would like to thank for the attention. All the results, or most of these results which I presented, are contained in a paper preprint, which will now appear as a chapter in this monograph, Springer monograph in July. Thank you very much for the attention.
Thank you very much.